Today's quiz involves resistance. Here I've got copper wire. Copper wire acts kind of like a tube or a pipe for electrons to go through. Therefore, we can use analogies of water through a garden hose, or you could even use people driving cars through tunnels. Aluminum, and this wire is about the same as that wire in terms of size, has a little bit more resistance. Actually, more than a little bit. It's nearly twice as much as the copper. So that's what our quiz is going to be about today, different configurations of wire and how the resistance is going to be affected by that configuration. So here's the quiz. We'd like you to rank those configurations in terms of the smallest overall amount of resistance and those that have the highest amount of resistance. In looking at our wires, we can see that the aluminum is going to end up being the white colored wire, and the orange or copper color is going to represent our copper. Right away, we can start to think, well, if this were a tunnel and it's the longest, we might think that that's going to have the most amount of resistance. The opposite end of the spectrum is going to be down here with E. And E, we would say, well, if that was a really short tunnel and it was really big, we'd be able to get through there quicker. Same thing with a garden hose. If I had water trying to get through this garden hose, it's going to certainly be a lot more difficult than if the hose was bigger and shorter. So right away, I think we can end up saying that this is going to end up having the most amount of resistance, and this would end up being the least. When we look at B, C, and D, well, again, we already told you that copper is going to have less resistance than the aluminum. And in this case, we know that we would end up having less resistance than the aluminum if everything else were the same, including the length and the cross-sectional area. But D is closer to E. While it has the same length as B and C, it is going to end up having a greater area. So if that's the case, we would probably say E, and then D, and then B, C, and A. So let's go ahead and put those up there. The smallest would be our E, and then we'd have our D, and then we'd be B, and then C, and then A. That would be our order. Now, if we wanted to go for a deeper dive, we could certainly do that. We could start to say, what are the factors that really influence the resistance? And we could certainly put resistance would be proportional to the length. So the longer it is, the more resistance we would have. We could also say what the material was. We already told you that aluminum has more resistance than the copper, so we could say resistance is also proportional to, we're going to use resistivity as the technical term here, and we give that a rho symbol. We also know as the area gets bigger, we have less resistance, so that would be an inverse. So we could say resistance is proportional to 1 over A. Now, if we put all those together, we could probably end up getting a formula. We'd probably be able to say resistance is therefore equal to our resistivity times our length all over our area. Now that we have that, you might want to even take a shot at displaying each of those configurations using this new formula. Give that a try. I'll give you a minute. All right, let's go ahead and talk about the different configurations. This has a very large length, this one small. These three are the same, but this one has a different area. A couple different ways that we can do this. We can end up using the size of the letter to indicate the size of the length or the area. So in this particular case, we have, we'll use the same formula each time. Here I have the resistivity, which is going to be bigger than the copper. So in this case, I would have a pretty big resistivity, a pretty big length, And in this case, I would have the smallest area. So I have a big times a big divided by a small. That's going to give us a very large resistance. On the other side of the spectrum, we can end up saying, well, this one down here has a big area, short length, and it's got a smaller resistivity. So in this case, I'll put my equal sign right here, and I'll say small resistivity, very small length, and I've got a really, really big area. And therefore, this would have a very small R. This next case here is going to be very similar to E. It's not quite as wide, but the length is equal to the three of these. So all three have the same length. In this case, I would say this one has the smaller resistivity. It's got a medium length and probably a medium area. And therefore, it's going to end up having a little bit more resistance than this bottom one. That leaves us now with these two, B and C. And while they have the same exact length, so I could put that for each of them, they both have, about the same length as this one, so I'll put a length and a length. Clearly smaller than that, but bigger than this one. This one has a smaller resistivity. This one has a bigger resistivity because it's aluminum. They both also have the same area. And that area is going to be a little bit smaller than these bigger ones and so on. So I could end up saying the area is just a little bit bigger for these. So I have an A and I'll have an A. Now what we could say is the aluminum would end up having a big times a medium, medium, and this one is going to end up having a slightly bigger resistance than this one here. I'll make that a little bit bigger. And it'll be just a little bit bigger than that. So again, we've got our E, and then our D, and then our B, our C, and our A. And that's your quiz with formulas that we can create just by knowing some basic proportionalities. All right.